it without the double angle properties and stuff, and I got the same answer.
Yeah,
just messier.
it's just
so
messier.
If you guys
Yeah.
don't know those, it's okay. It's just,
Right. Okay, here we go, y'all. Area of a polar region bound by r as a function of theta between a and b, okay, two different theta values. This is our formula for that area. 1/2 the integral from a to b of r
Can you erase the 4?
squared. Oh my, yes. D theta. Sorry about that. Where your limits here are between 0 and 2 pi, the difference between your limits. So this is the formula we're going to be using today, or some form of it, I'll put it that way. Now, we might get to the arc length problem. Hold on just a second. Yeah, we might. So let's talk about the arc length formula. On that formula sheet that you picked up on the first day, at the bottom, it had the speed formula, remember? Square root of. And then it has your parametric arc length, which is just the integral of the speed, okay? So it's different for this one. So polar arc length, write this down. Polar arc length. I'm going to say L is equal to the integral from a to b of the square root of r squared plus r prime squared. Remember, your parametric arc length formula was the integral from a to b of the square root of dx dt squared plus dy dt squared. You took your distance, that distance formula, the speed formula, but it gave you the magnitude. You took that and just integrated it to get the arc length. Okay, so let's look at this formula. This is what we're going to be working with today. To get those limits of integration, you're going to get them. There's several different ways you could get them. Okay, so let's talk about your limits. Your limits of integration, they will either be given. They rarely are given, but sometimes they are. Or you're going to use the graph and symmetry, which this is usually what I do because it's easier for me visually to use the graph and symmetry. Sometimes we're going to have to find the intersects of two curves. Find intersects of two curves. And then sometimes we need to find what we call the tangents at the pole. What's the pole on a polar grid? It's the origin. At the origin, what is your R? 0, because you haven't walked out any direction. So at the pole, that's where R is equal to 0. Okay? So sometimes you're going to have to find the tangents at the pole. In other words, find theta where r is equal to 0, but r prime is not equal to 0. Remember, if they're both equal to 0, it's inconclusive. Okay, here's our first problem. I'm going to just do this, get rid of all that. Problem number 1. It says, with a calculator, find the area of one petal of r equals 3 cosine 3 theta from 0 to pi. We graphed that yesterday in our notes, didn't we? That one we did. So let's graph that real quick. So we want area inside one petal.
Are you okay if I do that? It's just glaring.
Oh yeah, if it's easier, yeah, for sure, for sure. Of r equals 3 cosine 3 theta. 3 was our petal length. This 3 told us our petal length. This 3, since it's odd, tells me that's how many petals we've got, right? Okay, so I'm thinking, okay, we already know that one cycle of this was from 0 to pi, right? That's traced out the whole curve. Okay, so I'm thinking, well, we know that that curve looked like this, right? So we started here at 3, and we went this way, hit the pole, came down here, traced that petal, traced this one, and then we finished. That's what we did yesterday for this curve, right? For this one, I'm thinking, okay, well, when we started at 0, that was that point right there. And then at some point, we were at the pole, which was where r was equal to 0. So if we don't remember, let's just set this equal to 0. So 3 cosine 3 theta equals 0. It's when 3 theta is equal to pi over 2, 3 pi over 2. And I think that's as far as I really need to go for this one. So then theta is equal to pi over 6 and what? Pi over 2? We went out one more yesterday and found out that, okay, it hit that pole 3 times to trace this whole curve out. We don't need that. We want the area inside one petal, okay? So this pi over 6 right here is my first tangent at the pole. Right there is my first one, pi over 6. My next tangent at the pole is pi over 2, which is right here. So this right here is the petal that is between that pi over 6 and pi over 2. Do you see that? You good with that? Okay, so then let's use those tangents at the pole as our limits of integration. Okay, so here we go. Area is equal to 1/2 times the integral from pi over 6 to pi over 2 of r squared. So put that 3 cosine 3 theta, that whole thing, squared d theta. Grab your calculator and tell me what this is. Take it out 4 decimals for me.
Did you just use that pedal because it was just one we could get limits for?
Well, that's just, if I use my tangents at the pole, that's all the petals are the same size.
Yeah.
That's just the petal that those two tangents are, that is between those two tangents. Okay? But, so we're doing this method right here to find our limits. We're going to do something different here in a second, and you're going to plug it in your calculator and go, wow, I got the exact same thing. The symmetry is what I would have done on this one, okay? But we can use tangents at the pole. I want to just kind of get used to that. What do we get? 2 point something? 2.3561? Okay. Could we have, I know that at 0 I'm right here, right? Are you with me? And if I get 0 to pi over 6, I've drawn the top half of that petal, right? Well, if I integrate from 0 to pi over 6, I've got half a petal, yes? Mm-hmm. Well, could I just put those as my limits and double this? Let's try it. Write that down. So we're going to say, or area is equal to 2 times 1/2. We're going to integrate 0 to pi over 6 of this r squared. Put that in your calculator. Obviously, you don't have to put the 2 times 1/2 in your calculator, but I want that to be in your notes so that you can see, oh, we're using symmetry. Plug that in your calculator and tell me if you get the exact same decimal. Thumbs up if you got the same number. You got it? Awesome. So here's my other question. Could you have integrated from negative pi over 6 to positive pi over 6 and used your 1/2 integral of, you want to throw that in your calculator and see if you get the exact same? You don't have to, but you will. So there's a lot of different ways. If you know how this got graphed, you know that this is at 0 and this is at pi over 6, then you can use your tangents at the pole, okay, and just graph it that way. Not tangent at the pole, you could use the first tangent at the pole and then just use symmetry and double it. We good? Questions? We okay? All right. All right, this one's weird. This is a challenging one. We're going to draw two different curves here because they want, this came from an FRQ. Find the area of the region inside r equals 4 plus 4 cosine theta. 4 plus 4, a is equal to b. So a over b is 1. What's that the graph of?
Line.
It is a limicon. Which one? It's the
It's a cardioid.
a cardioid. It's the heart-shaped one. It has a little point here, okay? And then it wants the area inside that, but outside r equals 6. What is r equals 6? That's a circle. That's a circle. So I want us to graph this first, okay? So here's the thing. I know that cardioid, it's 4 plus 4 cosine, so we know it's going to be symmetric about the polar axis. 4 plus 4, 1, 2, 3, 4, 5, 6, 7, 8. And then, oh my goodness, I didn't give myself enough room. Here's 6. It's negative 6. 6. I'm going to draw my circle first, even though it's not going to look like a very good circle because my grid is off. Draw your r equals 6 first. Ooh, that's OA over there. It's not a good circle. So here is 4, negative 4. And I'm just doing this because I know that 4 plus 4 cosine theta at pi over 2, cosine of pi over 2 is 0, right? So it would be 4 plus 0 would be your r. So I'd be right here at pi over 2. And 3 pi over 2, I'd be down here. And I know that at 0, I'm at 8. 4 plus 4 cosine of 0 would be 4 plus 4 is 8. Okay, we know it's a cardioid. So you're going to go something like this, and it's going to hit that. Boom. Come back around. There you go. We want the area inside the cardioid, but outside of the circle. So this right here is the area that we want, right here. Shade that in. That's what we're looking for. All right. What method do you think we need to use here to find our limits for this one? We've got two different curves. Yeah, where do they intersect? That's exactly right. So I need to find out what is the theta when this happens right here. Okay, and this. But I'm thinking we might be able to use symmetry on this one too. Okay. All right, so then let's find those intersects. So I'm going to set 4 plus 4 cosine theta equal to what? 6. So then 4 cosine theta equals 2. So then cosine theta is equal to 1/2. What theta does that happen at? Pi over 3. And this one down here would be 5 pi over 3, right? Okay. So if I want the area inside 4 plus 4 cosine, but outside of the r equals 6, think about what that integrand is going to look like. Say it again?
Right minus left.
Well, you still want your r squared to get the area inside this cardioid, right? But if you go r squared here, you've got part of this, right? You don't want that. So you just have to subtract that area. So that would just be minus that r squared. that make sense? Okay, so then here we go. Area is equal to, oh, let's stop for a second. At theta equals 0, 4 plus 4 cosine of 0, that's 8, right? So that's where I started graphing my cardioid. You good? And from 0 to what? Pi over 3? Can I do that and double it so I don't have to do this twice? Okay. Or you could go, couldn't you go negative pi over 3 to positive pi over 3 and not double it? You could do either one. How about half of us, let's split the class in half. Y'all go from 0 to pi over 3 and double it. And y'all go from negative pi over 3 to positive pi over 3 and not double it. Okay, so the only thing that's different is our limits. Okay, I am going to go from 0 to pi over 3 and double it. So 2 times 1/2 integral 0 to pi over 3. And this is what we're going to do. We're going to do 4 plus 4 cosine, cosine, not theta, cosine theta squared minus 6 squared. That's going to give me the area inside my cardioid, and then I'm going to take away the area from 0 to pi over 3 that it grabbed inside my circle. I want to get rid of that. Okay? Put that in your calculator, or if you're doing the negative pi over 3 to positive pi over 3, don't put the 2, put the 1/2. Tell me what you got. Is that what you got? You got the 18?
Yeah.
6105? Is that what you got? Awesome. Okay, the next one we work is going to be arc length. Arc length of one petal of a rose. And then we're going to stop, and we will do 4, 5, and 6 next class. I like for us to have notes like this in here so that you can just see that there are different ways that you can visualize it and work through it and still get the same answer. We good? All right, number 3. Wants us to find the arc length of one petal. Okay, so we are looking for arc length of one petal of r equals cosine 2 theta. That's a rose. What's my petal length? 1. Is that a, the coefficient of your cosine? How many petals do I have? 4 petals, okay? So on this one, they're wanting the arc length of, I'm just going to say, okay, that petal right there. In other words, what is the length all the way around that petal? Arc length, we need r and we need r prime. So let's find, let's say r is equal to cosine 2 theta. And r prime is equal to what? What's the derivative of this? Yep, negative 2 sine 2 theta. So I know I'm going to just do square root of r squared plus r prime squared. I need my limits on this one. So set this equal to 0. And what do you get? Cosine 2 theta equals 0. When 2 theta is equal to pi over 2, 3 pi over 2. So then theta is equal to pi over 4, 3 pi over 4. That is when your curve will hit the pole, where r is 0, right? So when cosine is 0, your radius is what? What's the cosine of 0? 1. So I start this curve right here at 0. When's the first time I'm going to hit the pole? Pi over 4, right? So from 0 to pi over 4, I have half of my arc length, right? So then couldn't I just double that? Let's do that, okay? So then I'm going to say my arc length is equal to, there's no 1/2 in front of the arc length integral, okay? So don't do 1/2 times 2. It's just 2 times the integral from 0 to pi over 4 using symmetry of big square root cosine 2 theta squared plus negative 2 sine 2 theta squared d theta. What could I have done? I don't know, negative pi over 4 to positive pi over 4 and not doubled it? Yeah, for sure. Okay, throw that in your calculator and tell me what you get. We get that? Awesome. So here's the thing. When does class end? Like 5, 10 after, something like that? Okay. You have a few minutes that you can probably start on some of those test problems if you want to get those out. Okay? I would say get as far as you can on those.
I got
Okay.
an error. Can you see what I